Okay, so our second speaker this afternoon is Pelle Steffens from the University of Montpellier, and he's going to talk about field theory from a derived geometric perspective, global elliptic moduli problems. Please.
Thank you so much. Yeah, let me first say that this week has been an absolute pleasure. And yeah, I think, well, due to this devious switch that I made, it's now my honor to thank the organizers for making all this possible. And I don't know, I think we can all, if we can all give a sort of online applause to these wonderful people, that would be awesome. All right. Yeah, so I am going to talk about you know, some ideas in derived geometry, some ideas in field theory. Essentially, what I will do is repeat some of the things Alban said, but just much slower, and go into fewer depth, but we'll see how far we go. Okay, so if there's anything I would like you to take away from this talk is the following idea. So, well, what's going to happen in the following 4 slides? If this doesn't make much sense to you, that's fine, because the talk will be essentially about defining what is going on in these next slides. So, essentially, doing quantum field theory and studying the geometric structures on the Euler-Lagrange moduli space is difficult, because there are two sort of different kinds of singularities that we have to deal with. What could happen is that our action functional defined as a local functional on a space of sections of some vibration is not so its derivative, its functional derivatives might not be transverse to the 0 section. Right? We can view the variation of S as a section of some infinite dimensional cotangent space. And if the Hessian has degenerate points, then yeah, we will generally not have a smooth moduli space. And the other point is that, like, we may have some symmetries. Maybe Y is a product of M cross some other space. So we have some sigma model, and we have groups acting on the source and the target, or maybe we have some gauge theory. And in both cases, there may be internal symmetry points for our sort of certain points in the space of solutions may have non-trivial automorphisms. So in the framework I'm going to talk about here, we solve problem A by enlarging the one category of non-singular affine spaces, which in our case is smooth manifolds, to an infinity category of derived spaces, which are called the affine derived manifolds. And I will define what these are in due time. And problem B is solved by, well, as we've quickly seen in Alban's talk last time, so on this new notion of affines, we can take infinity sheaves, get some higher topos, and in there, that is a good place to study objects whose points have internal symmetries. And so what we do is we're gonna form Lie groupoid objects. So here x1 and x0 are both supposed to be affine. These maps are supposed to be smooth, and this object may not be representable. And then we can sort of iterate this, take another affine x1, but now take another affine x0, but now x1 may be an object such as we obtained here. And so iterating this leads to these higher geometric stacks. All right. In this new mathematical world, this higher topos, it's very easy to define moduli spaces relevant to field theory. For instance, we start with the data of a manifold, then we can view this as an object. So we can first view this as a derived manifold, and then we can view it as an object in sheaves on derived manifolds via the unit embedding, taking products determines a functor to the slice category. So this is where objects live, this is where things live which have an error 2m. And this map turns out to have a right adjoint. And this is instantiating, taking sections of things that live over here. So furthermore, we have some data. So we're going to define, so we want to consider nonlinear differential operators between bundles. So we take some submersive, surjective submersion. We're going to consider nonlinear differential operators with values in a vector bundle. So this factorization here, so we see a JKY, that's the kth jet bundle, which precisely means that it's a kth order differential operator. Then this differential operator induces a map between these stacks of sections. And then it's easy to demand that, like, that sort of to construct a space that is instantiating the derived intersection of P with the zero locus. So we take a homotopy pullback diagram in this in sheaves on derived affines. So in general, these mapping stacks here may be very large, maybe very wild, very difficult to analyze. But in good cases, this space here is in fact very tractable. So the most important thing I should convey to you today is that in good cases, so when M is compact, this object, the solution space, is in fact almost representable. It's not quite representable by an affine, but just basically representable by sort of scheme-like object. So it's constructed by gluing along equivalences of affines. If and only if you check a point-wise condition, you check that at each point, the space of solutions is in some sense finite dimensional. So this tangent complex here somehow controls the formal neighborhood of this space. And in this case, well, we're not doing anything stacky, so this will be a two-term complex, and it's the differential coincides precisely with the linearization of this operator. If this is elliptic, this complex is perfect, and it turns out that that is enough to produce an atlas by affines on this thing. And so here everything, well, let me go back quickly. Here everything happens without symmetry groups, but there is also equivariant versions. So you can do a gauge theory or symplectic topology and act by, say, holomorphic automorphisms of the domain of some complex surface. Okay, so if anything is unclear, also just put something in the chat. I'd be happy to answer questions during the talk. So, oh, this is unfortunate, something has fallen off, but so if these conditions are satisfied, then this quadruple is an elliptic moduli problem. And well, this terminology I somehow stole from Costello-Guilliam, but this is really a global version of what they study, because if you think about like what is BV field theory, it is essentially sort of taking this construction, but then forgetting you had a global picture there, and only look at the formal completion at a given solution, which is then controlled by this shifted tangent complex. So this, by formal nonsense, gets equipped with a Lie algebra structure. And these are precisely this, well, a DG Lie algebra structure, and these are precisely the elliptic L infinity algebras that Costello and Guilliam study. And so I believe this first point is actually currently under sort of, it's being investigated by Owen and David Carcady, but I'm not sure how far their work is along. And this is something I'm thinking about sort of at the moment. So if this partial differential equation actually comes from, is actually the Euler-Lagrange equations for some action functional, then this stack should admit a shifted symplectic structure. And going to the formal completion, this should equip this elliptic L-infinity algebra with the structure of a classical BV field theory. Yeah, but sort of you can imagine that this is not as easy as in derived algebraic geometry, since while this space may be representable, in the meanwhile, there's all these very large infinite dimensional stacks appearing. Okay, so if you're a bit lost at this point, or you have no idea what I said, that's completely fine, because the goal of the talk is to just define all these words. So we're going to do this in the following fashion. So first I'll outline some very brief infinity category theory. Then I would like to explain how to move in a sort of algorithmic way from non-singular geometry to derived geometry. Then I will talk a bit about this notion of going from affines to stacky objects, and then we, once all these notions have been absorbed, we go back to this representability theorem and see what it gets us. Okay, so for me, an infinity category is well, it's just some homotopy gadget that allows you to take higher morphisms for any level, but here I'd like to think of this as a quasi-category. So that's just a simplicial set which has the right lifting property with respect to all inner horns, and this is a very convenient model. Well, not because so precisely because it's quite hard to write down sort of quasi-categories by hand. It's actually the machinery of quasi-categories makes them easy to work with. And well, there's just a few categories we need. So there's the infinity category of spaces, or infinity groupoids, that we all probably are familiar with. Yeah. So I will do this a couple of times. So if you have an infinity category equipped with some kind of Grothendieck topology, we can consider sheaves. If you take, say, E-infinity algebra objects in K modules, or K some commutative ring, there's a category of unbounded commutative K algebras, and its connective part has an interesting model that will be very useful later. So I will quickly explain it now. So consider the category of that I'm going to call poly K. So its objects are just products of affine K space. So K0, K1, K2, etc. And its morphisms are polynomial maps. Then it turns out that if you take, so this little pi here means product preserving. So if you take product preserving functors from this category into spaces, this exactly models connective commutative K algebras. So how should you think about this? Well, what does such a functor give you? So suppose you have such an A. You have then a space, A applied to K, which determines all other values of the category because A is product preserving. And then all the polynomial maps determine for you sort of functorial or sort of homotopy coherent operations between A to the N to A to the M for every polynomial map. And if you do this, say, not for spaces, but for sets, it's very easy to see that this is precisely, that to get these operations, you precisely need a commutative K algebra structure on A. In the infinity categorical sense, it's a monadicity argument, but it holds true nevertheless. Okay, so we have our setup. Now we want to think about doing derived geometry. So in the introduction, I tried to motivate this by sort of appealing to, well, we have these infinite dimensional transversality problems, and we're going to resolve this by first dealing with finite dimensional lack of transversality, and then taking sheaves on these. So it turns out that there's actually a very algorithmic universal way of going from some some setting where you have non-singular smooth spaces to an infinity category of derived spaces. So for us, we're mostly concerned with this category of smooth manifolds. But to compare, we also maybe like to consider the category of open subschemes of affine K-space. And these categories do not have finite limits. So you cannot take arbitrary intersections of smooth spaces. And this is precisely the problem we'd like to fix. So while there are many intersections that do not exist, or intersections that do exist but do not have sort of the right geometric property. So yeah, if you say like intersect a line with itself, well, that's again an object in your category, but this somehow should, this object doesn't have the right dimension. It should somehow lose a dimension, while in this sort of doing it naively, the dimension stays the same. So in both these categories, there is a notion of, there's a collection of pullback diagrams which do have all the geometric properties we like. So in the category of manifolds, those are simply transverse intersections. And for open subschemes, you can take say open embeddings between these objects. So with this data in hand, we can then try to do the following. So we take this category T, and we're going to enlarge it in a specific way. We're going to add all finite limits with the condition that the transversal pullback diagrams, these good pullbacks, that those do not change. And we want to do this in a universal way. So I've said it here very sketchily, but this procedure is well defined. G has a universal property in a certain full subcategory of the infinity 2 category of infinity categories. And if we do this for, via this procedure, we start with some notion of non-singular space, and we obtain then some associated notion of derived geometry. So conceptually, this is very, very satisfying, very appealing, but it doesn't give you much unless you can actually relate G to something you're familiar with. So here's a theorem I should say this whole procedure of going from something smooth to something derived is due to Lurie. Or maybe there's antecedents that I'm not aware of, but you can find it in one of his DAG papers. And what he proves there is that if you indeed take this sort of algebraic geometry of open subschemes of a fine K-space, then the geometry you associate is precisely this category, is precisely a certain full subcategory of this category of simplicial commutative rings, so connective commutative K algebras. And finitely presented here means homotopically finitely presented. So these should be compact objects in connective commutative K algebras. Okay, so this is even more satisfying. Like we obtain we don't even need to make an ansatz or do something ad hoc to recover derived algebraic geometry from smooth non-singular algebraic geometry over K. Okay, so what happens for this other category? So if we take manifolds where the good pullbacks are the transversal ones, well, we're going to obtain a similar sort of algebraic gadget, but this algebraic gadget will encode the smoothness of the objects we're supposed to be working with. So we're going to make a very similar definition to this poly K category. So we're going to define Cartesian spaces as the categories objects are Euclidean spaces for so Rk for k greater or equal than 0, and morphisms are just all smooth maps. And then we can do exactly the same procedure. So we define a category of simplicial C-infinity rings, not commutative R algebras, but C-infinity rings, as product preserving functors out of, oh wait, there's an op here which should not be there. Disregard this op, then it's correct. And so what you should think of, how you should think of this is actually some sort of commutative algebra, but somehow for every smooth map, you have an extra operation. So these are sort of algebras these are commutative algebras that are equipped with some sort of smooth functional calculus. Well, up to coherent homotopy in this infinity categorical setting. So here's some facts about this infinity category that we just defined. So there's an obvious functor taking manifolds to these simplicial C-infinity rings. By just taking smooth functions, it's obvious that if you take smooth functions on a manifold, you can then compose with any smooth function on Rn. Like I said, like you can forget this extra C-infinity structure and just obtain another, and just obtain an underlying commutative R algebra, which reflects equivalences, preserves limits, and sifted colimits. And yeah, as such, it has a left adjoint, which is in general rather opaque, but on polynomial, so it sends polynomial algebras here to C-infinity of Rn over here. The most important property is that the coproduct in this infinity category somehow behaves as a completed tensor product. But we needn't go to any sort of world of topological or bornological algebras. This just follows from the basic category theory here. So this statement here is relatively easy. This statement here is much more work. But once one has proven this, it is not very hard to show that you can then characterize the full subcategory of these simplicial C-infinity rings on the ones that are finitely presented as the associated derived geometry of the category of manifolds with these good transverse pullbacks. So a little word about like, okay, what are homotopically finitely presented objects here? They can be characterized by taking these objects in the essential image of the unate embedding, and then just taking arbitrary finite colimits, or dually, if you think about them geometrically, arbitrary finite limits, and taking retracts of those. Okay. Oh, that's unfortunate. I thought I had a slide here that made a connection with a much more algebraic version of this, of these simplicial C-infinity rings. Maybe I'll just say it in words. So it turns out that actually you can yeah, it turns out there's a much more tractable algebraic category that you can use. So you can take, say, CDGAs in, say, homologically non-negative degree, and then demand that only on in degree 0, there's a C-infinity ring structure in sets. So localizing these at the obvious notion of weak equivalences also recovers this category that controls derived differential geometry. And using this model, it's very easy to see that all DG manifolds, or all, I don't know what the terminology is, all N and Q, no, I think N supermanifolds are in fact such affine derived manifolds, right? So we set derived C infinity affine as the opposite of compact objects, finitely presented objects in simplicial C infinity rings. Okay, so this representability theorem I showed you in the first slide. So it says that, like, when we look for the spaces of solutions of differential equations, we cannot expect that they will be affine, but they will be somehow glued via affines along equivalences. And to define these spaces, you just think very algebra geometrically with this category. So you can define an infinity. So when I say define an infinity category in objects and morphisms, of course, there's a lot more work involved. But I think for the purposes of this talk and this audience, this will suffice. So these are simply like locally ring spaces. These are pairs of a topological space together with a sheaf of rings, but this is now a sheaf of simplicial C infinity rings. And these stalks, they have to be as usual local rings, but because there's this extra C infinity structure, it turns out that you have to demand that your residue field is always the reals. And actually that implies that all the maps will automatically be local rings. So and a map is the usual thing. So here, to make everything work out, I think, yeah, so a map from XOX to YOY is a map on topological spaces from Y to X, together with a morphism from the push forward. So this, from this definition of morphisms, it's easy to see that this is a Grothendieck fibration or a co-Cartesian fibration over the opposite category of topological spaces. Yeah, so before I continue, I might say that, like, there is actually a much more general version of such infinity categories of locally ringed spaces. You needn't start with a topological space. You can just think of OX as an object in sheaves on X, and then you can replace X or these category of opens of X with an arbitrary infinity category that has a topology. So those will give you locally ringed topoi. And yeah, these allow you to not only glue along equivalences, but also glue along local equivalences. So say local diffeomorphisms. Okay. Yeah, so how do you relate these affine guys to these locally ringed spaces? Well, as in the algebraic version, there is a spectrum global sections adjunction, which turns out to be an equivalence on this category of derived C infinity affines. And if you want to know what it does, it's so remember, so P was the underlying space functor of spec A. This is the maximal ideal spectrum, but the residue field needs to be the reals. And if you take A, say C infinity of a manifold, it's very easy to see that pi zero this spec of C infinity of M actually gives you back the space M. And the structure sheaf is easy to define because all open sets are identified with localizations. So so again, if A is C infinity of M, and you have some smooth function in the manifold, you can localize it. You ask where it's non-zero. That gives you smooth functions on this open set. That's this localization map. And the structure sheaf simply sends, to that just assigns the localization to the open set determined by that localization, and then sheafifies. Okay. So now we can define in this category of derived C infinity affines a derived manifold, which is essentially the same definition that Spivak gave. You add some topological properties to your space, and then demand that locally it's equivalent to spec A for some derived C infinity affine A. And well, as I've argued before, an elliptic moduli problem on a compact manifold without symmetries always has such a structure. And sort of, there's a slight subtlety with the statement. So, what does this mean? Well, it turns out that the Yoneda embedding that goes from derived C infinity affines into sheaves on those. So these are then these derived C infinity stacks. That actually factors through through derived manifolds in a fully faithful manner. So how should you think of this? This essentially means that you can either glue derived manifolds either glue affines together in this category of locally ring spaces, or you do it in this higher topos, and the result is the same. So if we like to glue along more general things than local equivalences, than equivalences, say we want to do local equivalences, that is possible. Then you have to work with this more general notion of locally ring spaces, where you replace your space by topos. And this theorem, this proposition still holds. It becomes a much more powerful statement, but indeed, take I don't know what this would be called, like a derived Deligne-Mumford stack would be a pair where you have not a space here, but sheaves on a category. And together with a sheaf of simplicial C infinity rings in this topos, which is locally equivalent to spec A. And that still maps fully faithfully in this topos. If you want to glue along submersions, so locally you project away k smooth directions, then this category of locally ring spaces does not suffice anymore, and we have to pass to Artin stacks. And this precisely happens when we want to do when we want to when we want to do Seiberg-Witten theory, or consider moduli spaces of anti-self-dual connections, or Chern-Simons theory, those will be non-trivially stacky. So how do you define that kind of gluing? Well, a inductive definition of such an object was, I think, first given by Simpson. Probably it goes back to Grothendieck as usual. So what happens is you start at level -1, and that's simply derived manifold. And then you start taking colimits of groupoid objects. So x0 and x1 here are supposed to be derived manifolds, and f is supposed to be a submersion, which determines it's a groupoid object. So all these other terms in this colimit diagram are determined. You take the colimit, this object is a zero Artin stack. And then you inductively continue, and I'm being a little bit, I'm cheating here somewhat, because you do not only have to inductively define the objects, but you also have to inductively define the notion of a smooth morphism. So when I say f is a smooth morphism, it's actually, again, disappeared behind this, behind my slide. But yeah, so what should happen here is y naught is a -1 Artin stack. So that's just a derived manifold. And now the space of morphisms of your groupoid is an n Artin stack defined by induction, and f is a smooth morphism. So you should think of this as, so this should also be y naught quotiented by y1. So how should you think of this? Well, if you know what an n Artin stack is, you sort of know what an n groupoid object is, and you also know what an n group object is. And you notice that if you have an affine object, you have a derived manifold, you act on it with an n group, and you take the quotient. This is not in general, again, an n Artin stack. So doing that procedure, taking that further quotient, takes you takes you one level further into n+1 Artin stacks. Okay. So let me give some examples here. So there's many obvious ones. So it turns out that if the functor from manifolds into derived C-infinity affines is fully faithful. This is in fact not entirely obvious. And it induces an adjoint pair where I upper star is simply pulling back sheaves, and I lower shriek is taking left Kahn extensions. And somewhat, well, this is also not quite obvious, but this functor turns out to be fully faithful, and it preserves finite products. And it turns out that much of this topic is actually sort of a lot of the theorems in this topic depend on further properties of this pullback function, this push forward functor here. So if you want to prove some of the theorems that I have mentioned, you need to know exactly which pullback diagrams in here are preserved by this functor. Well, in any case, as a consequence of this result, all higher Lie groupoids that we already had in sheaves on manifolds, so all classifying stacks of groups, all classifying stacks of n-gerbs become also derived stacks in a trivial way. There are interesting examples of stacks which are both higher and derived. So that's, for instance, this stack of perfect complexes, which you should view as assigning to a derived manifold the space of chain complexes of vector bundles, sort of sitting between degrees A and B. And if A is sufficiently negative and B is positive, then this is both higher and derived. I'm not aware of that many other examples of really higher Artin stacks, sort of apart from iterating these constructions, or say taking a tangent stack to a stack which is already Artin and then sort of shifting it further. But the representability theorems that I will mention again later actually produce some of these things. So this is the same. So now we come back to this representability theorem. And so now I hope that all the players in this diagram make sense. And what I should say about this is that, so let me see, how should I say this? Yeah, sort of the reason one should be happy with this result is that to define this space of solutions, at no point did I use a word like Frechet space or Banach manifold, or any of the terminology that usually comes with doing sort of looking at the global geometry of these moduli spaces. And that's an upshot, because in sort of other approaches to these sorts of to this sort of geometry, what people do is they start with the set of solutions of the differential equation and then ask, okay, what kind of structure can we put on this? Is it a manifold? Is it maybe something slightly more general? And somehow that move already handicaps you a little bit, because as you see from this perspective, it is already clear what the structure of this object is. It's a derived stack. Then what we sort of, to make sure that this is somehow like a reasonable geometric space, we ask, does it have a certain property? Sort of, does it lie in a certain subcategory of sheaves on derived affines? And yeah, that shift in perspective gains you a lot of conceptual ground. Sort of, okay, maybe you lose some concreteness because you have to go to this higher categorical world. But you should sort of view it as like, well, if I give you a topological space and I ask, is this a smooth manifold? You have to start putting atlases on the space. You have to check whether certain transition functions, whether they're all smoothly compatible. You may have different smooth structures. However, if I just give you topological space and ask you, is this a topological manifold? The question is much easier. You just find an open cover by things that locally look like Rn. And this is somehow, an instantiation of that philosophy, that you sort of promotes property over structure. Well, from a certain perspective. Okay, so what kind of things can you do with such a result? Well, I will be really brief. I'll just give two small examples, but there are many, many more because there are many, many of these elliptic moduli problems. So one thing you could do is you could take a complex surface and think about the topological string theory with values in some symplectic manifold. Maybe you want to compute symplectic Gromov-Witten invariance. Sort of the classical approaches to this problem say, okay, take a certain Banach manifold of sections, apply a differential operator that takes you to another Banach manifold of sections, and hope that the results sort of intersecting this section that's given by the pseudo-holomorphic curve equation that determines a section between these Banach manifolds, hope that that is a smooth manifold. And if it's not, you're sort of in trouble. But from this perspective, you are never in trouble, because this representability theorem guarantees you that, well, for one, this object has a nice structure. It's a derived to infinity stack. And two, there are atlases for these things. And from this, following this approach, it's really it's really trivial to sort of go from pseudo-holomorphic maps to pseudo-holomorphic curves. So what does this mean? It means that you, instead of looking at all maps from your surface to X, which are holomorphic, you also quotient by the automorphisms of this source. And if you work in a Banach manifold setting, that is really difficult to accomplish. Because in a Banach manifold setting, you always lose some. You're never at your functions or sections are never smooth. To get Banachness, somehow you always need to restrict to some finite regularity, and that really messes up the fact that you even have this action. But in this setting, there is no problem at all. Everything works functorially. And by definition, such bases are derived zero-Artin stacks. So if you do gauge theory, so one example, say anti-self-dual connections on a Riemannian 4 manifold, you notice that this does not quite fall into the setup that I described here, because there's no mention of any group acting here, but sort of the representability result still holds. It's just a little less neat and tidy to write down. But indeed, you can find slices for this gauge group action and prove that it is a derived zero Artin stack. And I think, yes. And so I think I have no more slides. So let me just say that, you know, from the talk we just heard from Albin, we know that, you know, from these geometric stacks, these are the spaces that have good geometric properties. So these are spaces that have tangent spaces, tangent complexes, cotangent complexes. For all these things, you should be able to do shifted symplectic geometry. As I sketched in the introduction, there is even a way to produce virtual classes, say in this example, which is relevant to chromafitting theory. And yes, I think that is indeed where I will stop. Did I go over time? No, I think it's fine.
It is, yeah, so it's fine. You also started a bit late, but yeah, so let us, well, thank Pelle for a great talk. And yeah, so it's time for questions, but maybe before, I mean, please raise your hand if you have questions, but there was actually something in the chat.
Oh, I didn't see.
Yeah, so I think that was on slide 8.
Slide 8, where is slide 8?
Go to slide 8, and so Severin asked, why does this only describe connective commutative algebra? So that was like.
Yeah, so in general, so if you take things with values in spaces, you sort of always lack co-connective directions. So this infinity category of commutative K algebras is, well, if you do it completely infinity categorically, you take algebras for the commutative infinity operad. Say, well, first you take it in spectra, and in spectra there's the Eilenberg-MacLane spectrum of this K algebra. And yeah, this category is then also commutative algebras in non-connective K modules. So yeah, so I don't know if I'm explaining this very well.
No, I think that's okay.
Yeah.
Also.
Okay. Maybe I don't know. Maybe I'll think of something.
No,
clever to say later.
Alex. In the meantime, Alex also pointed out that it's the Dode-Kahn correspondence from simplicial to chains only gives connective things.
Yeah, that's true. That's true.
So, yeah, I think it's from there. But so may I ask another question? Is that okay?
I don't know if Eugene or Alex are not.
I think we have. I mean, we have time, so we can go through all the questions.
Okay.
So
cool.
Sure, go.
Maybe if you, I think it was on the slide where you first showed your representability.
Yes.
Theorem.
Here. Yes.
Yes, that one. So which statement was it? There was in. Right. So in statement C, there's suddenly a mention of an elliptic operator.
Yes. Yes. Yeah. So there is a subtlety.
But could you just comment on how from statements? I don't know. Well, but so P
so
is
C to B seems
right?
reasonable, right?
Yeah, so P is already assumed to be elliptic, right? So is that how the elliptic?
No. So P is not assumed to be elliptic. So a nonlinear elliptic operator is a nonlinear operator is just by definition elliptic, if and only if all its linearizations are elliptic. And it's so in linear. If you have a linear operator between sections of vector bundles, it turns out that ellipticity is equivalent to Fred wholeness, which in turn is equivalent to asking that the cohomology of the sort of two-term complex is perfect.
Okay. Yes.
So, but this is not this is something you can find in, I don't know.
And then for longer chain complexes with differential operators, there's a similar statement.
I think it's still true. I think there's always this trick you can do where you make it into a one-term complex by just summing all the even and odd parts.
Yes,
I think that would work here.
Okay. Yes. Okay. Cool. Yeah. Thank you.
No problem.
Okay. So next question, Alex, please.
Oh, hi. Thanks a lot for the talk. Can you go one slide back or backward? Yeah.
Yeah.
So the way how you define your solution space / stack is as the kernel of the equation of motion or of the PDE. Mm-hmm. So yeah, in a set theoretic world, that's of course the same as the critical locus of an action function when you have that. Are you sure that in full generality, this gives the same space? I mean, I give you now an action, which when you vary it gives P. Do you know that this sol P is the critical locus of this action?
Yeah, but because taking pullbacks commute with taking sort of the underlying topological space of these stacks somehow.
Okay, because the reason I'm asking is many years ago, I looked once at an example where I took the Young-Mills equation and I computed this kernel of the Young-Mills operator, not as derived stacks, but as non-derived stacks. And there it was very important to take as the 0 point, which you want to kind of, where you want to pick out the kernel, you have to take the stabilizers of the 0 point into account. Because otherwise you get the kind. So instead of the point star in the lower left corner, you should, when you have symmetries acting, also probably take the
yeah, you're absolutely right. So if you have symmetries like this looks a bit weird because then like this space down, you can still see my cursor, I hope.
Yeah.
So this space down here would have to somehow be, you know, invariant for this this action. I just wrote this statement because this is the most basic form of these type of results. So all these results, I mean, they what I think is neat is sort of they look somehow very they have somehow some sort of closed form. You don't mention any analysis, but it sort of, to of course prove these things, a lot of analysis has to happen in the background. And yeah, so this is why like the sort of gauge theory result is a bit more annoying to state, because then sort of you have to demand that slices exist for the gauge group action in order to produce these atlases on these produce these sort of Artin atlases. And that sort of tends to be not so clean.
So summing up, you say that what you call sol P, when P comes from an action, you can relate it to the critical locus. It's the same derived stack.
Yes. So, but you wouldn't, if P comes from an action, it would, this diagram would look a little different, right? You would have another term here, and you would have like the maps to sort of, so then you would sort of do some, you have to do some variational, you have to, sort of work in a setting where you can do sort of the variational bicomplex formalism in this derived world, in this sort of derived stacky world, which is possible. And then sort of, you don't take the cotangent of the maps, but you take the maps into the relative cotangent of this guy.
That is clear how the critical locus looks like. So you say you can show via variational techniques in this derived.
But sort of, that is the correct space. But the proof of the fact that it's representable, which goes like through, like
this of course gets harder when you have symmetries acting and stuff like that.
If you have symmetries, yes. If you just have a critical locus, it's not particularly harder, because sort of locally on the stacks, you can reduce to a diagram of this form.
Okay, nice. Yeah, thanks.
Thanks for the question. So there's one more by Eugene.
Yeah, thanks for the talk, Pelle. I was just wondering if you could describe this derived manifold sol P a little bit more? Like,
yeah, okay, I can say a couple of things.
So, ringed space, right?
Sorry?
It's supposed to be a locally ringed space, is that right?
Yes. Yeah, so it's a bit unfortunate, sort of. That I was struggling with my slides a bit, and with so I had I think a nicer version of this presentation, which had a bunch of slides that also gave much more explicit algebraic models for these sorts of things. So somehow locally, you know, at least in this simple situation, so this is always a one quasi-smooth object. So locally, this is always there's always a manifold with a vector bundle and a section, such that this is the derived zero locus of that section, so at least locally. So you can always model it as sort of the causal as a causal complex, where you take exterior powers of this vector bundle and then have the differential be this wedging, sort of taking sort of interior, taking the interior product with this section.
Mm-hmm.
Yeah. So how would you work with this? So yeah. Unfortunately, there's little time. So I don't know. Maybe I should explain this in the Corinne just told me there's endless time, so I don't know what.
Okay, maybe not endless time, but I mean, you can. I think.
Yeah. So what you how would you work with these things? Well, sort of the point is somehow that oftentimes the actual form of the atlas or sort of the atlas by some some derived and then affine guy and something that acts by symmetries, that is not so important. It's just what you need more often is that there is an atlas, because that allows you to sort of to go very often from sort of local computations to pointwise computations. So you don't understand the neighborhood of a single point in this thing very well. That's something that comes from like some deep functional analysis theorem. But at a point you understand it perfectly, because that's the cotangent complex is simply the dual of the elliptic complex. That determines this field theory at this point. So, you know, if you have sort of maps between these objects, it might be difficult to sort of, you know, if you didn't know that they actually had these atlases, it would be difficult to compare them directly. But because you know they have atlases, you know that actually it suffices to check that, say, their tangent complexes at a given point coincide. So there's abstract theory that tells you that, like, in the presence of an atlas, it's much easier. You know, you have much more tools to check that certain things are, I don't know, equivalent or, you know, étale or submersive or that sort of thing. I'm not sure you don't seem particularly convinced, but it's.
Well, I'm just processing what you're saying. So you're saying the particular structure as a derived manifold doesn't matter, but the fact that it is a derived manifold allows you basically to prove theorems just knowing the like formal information around the point at each point.
Yeah. So I would object a bit to the sort of the particular structure of it. So yeah, of course, maybe you don't say this. I don't know. Maybe you don't mean much by it, but like the point is precisely that the structure is determined. It's this atlas on it is a property, and you could just pick some other atlas. But the fact that there exists one, that's the relevant information. And yeah, so it's not just a particular feature of this setup, but it's sort of, yeah, it's if you're working with finitely presented objects in derived algebraic geometry or derived C-infinity geometry, you can prove it's, I don't know, it's essentially just the inverse function theorem, and play around with Nakayama's lemma a little bit. That's, you know, say that sort of a, well, let me give an example. So if you would know that the cotangent complex of this object is free at a given point, so it has no cohomology, it only has something in degree 0, then you would know that there's a neighborhood in this space that is a smooth manifold.
Mm-hmm.
Yeah, so being smooth at a point means you're smooth in a neighborhood of a point.
Mm-hmm.
And before you had this representability result, you had no idea what this is just some arbitrary sheaf.
I see.
I hope I'm
I think that makes sense.
Making something clear.
Yeah. Thank you.
Okay, so if there are, for the moment, no further questions, then let us thank Pelle again. And I will start.